Morning everyone. So we're going to continue our study in our periodicity unit so far. Up to this point here, we've been seeing a lot of patterns that are emerging on the periodic table. So far we know our metals on the left hand side, they're divided by the stair-step line. We have our non-metals on the right hand side. We've looked at some physical characteristics like your metallic character increases as you go into this corner. Metals tend to want to react by losing electrons. So as ionization energy drops and radius increases, they tend to be more reactive. We had a lot of patterns already emerge based on organizing the periodic table in this fashion. For today's lesson here, we're just going to switch over to some periodic trends which exist for compounds, so not just the elements themselves, and we're going to specifically look at compounds that contain oxygen, which are called oxides. Oxides are, so your non-metal is just going to be the O here. We're going to, in general, talk about metals bonded with oxygens. Those are typically going to be ionic compounds, or versus non-metals comparing to oxygen, those are typically going to be covalent compounds. And we'll see some general trends for the compounds themselves. So just generalizing more so, not just the properties of the elements themselves when they're pure, but also a trend going across this periodic table, comparing metal oxides. We're going to specifically go over period 3. So we're going to look at, let's say, sodium with oxide and magnesium with oxide. We're going to skip over, we're not going to bother with argon oxide because argon oxide is a noble gas, so argon doesn't really bond to oxide, but it's definitely going to compare it to things like we have phosphorus, sulfur, and chlorine. Those guys there will bond with oxide, and they'll also get the in-betweens. So I've typed out some of these notes for you as well, so as you listen through this lesson, it might be good just to print off the copy of our notes, and then we can scribble over it as we go through. So this section here is on period 3 oxides. Before we get into the actual row 3, we're going to look at oxides in general. I mentioned already oxides are chemicals that are bonded to oxygen. One thing you need to learn about these oxides is one feature is they're either going to be acidic, basic, or amphoteric. So acidic, if you remember your definition here, this is actually called the Arrhenius definition. For acids, they're able to release H plus in solution. When you drop them in water, they end up releasing this proton. Now one close look here at hydrogen here. On our periodic table, we have hydrogen, element number 1, and molar mass 1.01 as the weighted average. The 1 there stands for 1 proton. Notice hydrogen, strangely enough, the most stable isotope, only has the 1 proton. It actually has no neutrons. So in this case here, if I look at the H as an atom, I'm going to have that 1 proton in the core, and I'm going to have the electrons supposedly in orbit in that first shell. That's their ground state. That so far is the H atom. That's not my H plus yet. What do I need to do to this H atom to then make it an H plus? Hopefully you're going to tell me you want to lose the electron here. I still want to stay as H, so I don't want to touch the proton part. But I'm going to come with my pair of tweezers, grab the one and only electron that I see and completely remove it. And then I'm going to be left with just the H plus here. Definitely still positive because I have a proton. I want to just comment on the radius here. You'll notice that the radius has gone from being the size of being one whole shell out, that's for H atom, and suddenly now I'm just the radius of a proton. In fact, an H plus is synonymous with a proton. Charges in general aren't very stable, so especially when we get dropped into solution, the H plus doesn't last very long as this, just a single proton like this. Water very quickly comes around here. We introduced this term here called ligands in the last lesson, but water as an example of a ligand. Although overall water is neutral, it can't get rid of the plus charge that the hydrogen actually has. Water can actually donate its lone pair to actually bond with the hydrogen. Because both electrons in the covalent bond are coming from one neighbor, we're going to call that there a coordinate bond. More on this in tomorrow's lesson. And basically H plus ends up forming a complex ion. So try to color code this for you here. We're actually going to have H3O. And overall it's a plus charge. Again, water can't get rid of that plus charge, but like that hot potato example, instead of the positive charge just being held by the H plus, at least that positive charge, I can pass that hot potato around and I can spread out my charge so that overall we can carry that charge together. So especially as we do our acid-base chapter next year, we're going to see H plus is synonymous with the proton, and H plus in solution is actually an H3O plus, and we're going to call that guy either a hydrated proton or a hydronium ion. So most of your polyatomics that you memorize, hopefully by now, they used to be negative. We only had one that was positive, NH4 plus. Here's our second example. Again, this is called the Arrhenius definition. None of this fanciness for Arrhenius base. A base is supposed to give off the characteristic OH minus, also in solution. Pretty much we want to see some element with hydroxide, sodium hydroxide, lithium hydroxide. Those can be basic. So I just define it for you here: release proton, release hydroxide, amphoteric, or even the word amphiprotic we're going to see later on. Amphoteric has the notion, well, because some are acids and some are bases, amphoteric chemicals can actually be either acid or base. So we're going to see that more so on the back side. What's an example of oxide that's amphoteric? Again, in this section, unfortunately, it's fair game for them to actually ask you, here are the reactants, just predict the products. For a lot of them, you can just predict it based on what we've done before. Oh, it's a synthesis reaction. Oh, it's a single place reaction. You might be able to do it without memorizing, but for some of them, you just have to memorize. Not the end of the world if you can't quote it, but it is fair game for them to actually ask you that question. Throughout this chapter, we've been a little bit sloppy with the term like alkalis and bases. In fact, the term bases, like we just defined, releasing off hydroxide in solution, and alkali, like alkali metal or an alkaline earth metal, an alkali is a subset of bases, and these are specifically ones that are actually soluble in water. Now, in most cases, we do see the base release hydroxide when it's in water, but as we get to more general definitions like Bronsted-Lowry, like Lewis definition for base, we're going to totally even ignore the fact it has to produce hydroxide, but it's actually going to eventually have to do with electron transfers. More on this next year, but basically for now, we can treat alkalis and bases as the same thing, but remember, alkalis are the things that are soluble. In general, I just memorized here metals themselves and even their oxides in general. Metals tend to form base solutions, whereas nonmetals tend to form acidic solutions. Just a generalization, how come metals, or in this case here metal oxides, form bases? Because metal oxides are typically going to be ionic in nature. Let's say I have the calcium oxide here. What's going to end up happening is this is going to dissociate to form calcium ions and O-2 ions. Water is really good at chopping up ionic compounds because it can stabilize the bits. I really want this O2- because we're going to find very shortly this O2- is actually a strong base. It's really good as a base. It's really good at releasing the hydroxide in solution. So as long as we're ionic, as long as we can get that O2-, we're definitely going to be basic. Whereas non-metal oxide, typically called molecular as well, or because they're covalently bonded, you can for sure dissolve them into water. Most of them are going to be soluble. You can manage to capture some in the liquid, but because it is covalent, let's say CO2, we'll draw these pictures in the next chapter here. CO2 is actually double bonded. Water is not good enough to actually come and actually break this bond. I can't release the O-2, and because I can't do that, I end up doing some fancy synthesis reaction. It's like CO2 joins together with the water, and we end up forming H2CO3 instead. So if we're ionic, we form that O-2, we're a base. Because we form a base, we can even do a neutralization reaction. Bases are supposed to react with acids. Even though the oxide has yet to generate the hydroxide, I know that when you drop this in water, this is going to eventually create the hydroxide, and it's the OH- that reacts in a 1-to-1 ratio with H+. During a neutralization, we end up forming water. Right? So that's a generalization here. In fact, the more ionic something gets, the more basic the solution should be. To analyze this in a little more detail, again, as I mentioned, we're not going to look at sort of all metals in general. We're going to just focus on the row 3 elements. Starting off with the metal oxides first, then we'll jump over to the non-metal oxides, and on the back side, we'll come back and we'll look at the in-between. So, specifically, the period 3 oxides, sodium oxide, magnesium oxide, I mentioned already they're a giant ionic structure. That's where you get the lattice structure from. So let's say I have Na2O. I know by ratio, that means I have Na+, Na+. I need 2 Nas to counterbalance the oxygen's charge. But because this is a lattice, even though that's all I need to counterbalance my charges to have an overall net charge of 0, because charges are always attracted to the opposite sign, I can actually combine it with another Na+, another Na+, even though every compound, every what we call formula unit, it's like an empirical formula, every Lego block is roughly stable, we're going to have this negative not only wants its own positive neighbors, it's going to surround itself with as many other positive neighbors as possible, and that repeating fashion is ending up calling a lattice. A lattice is a structure that has alternating positive and negative charges. We rely on an electron transfer. So sodium used to have an electron. Here's oxygen. Looking at the sizes, the sodium has a lower Z effective. Oxygen has a higher Z effective here. These two here collide, so it's the outer electrons that actually potentially can be shared. Because oxygen here is more electronegative, we look at the tug-of-war. Oxygen pulls much harder than sodium does, more than that 1.8 that we usually throw around. The electron completely goes towards the oxygen side. In that case there, the sodium is now without the electron. It's totally cool losing that electron because now it reverts down to shell. We know all the inside shells are definitely full. The oxygen is a little bit closer to being happy. It's now been electron affinitied. It's now grabbed the first electron. It now wants to gain one more sodium. It steals the electron from one other sodium to finally complete it. Although when we did our electron affinity stuff, we saw that that second one is actually endothermic, even though we do end up getting that full shell noble gas stability. Because I was already negative, I don't necessarily want to gain that electron easily to become a negative 2. So a lot of competing features here, but ultimately this forms an ionic compound. The ionic character then, this electron transferability, would depend on the electron activity difference. I know it's going to be bigger than 1.8 in general for electrons to transfer, but what if the difference was 2 versus a difference of 3, a difference of 4? As the electron transfers become more dramatic, we end up becoming more ionic. The reason why in this case here we get more dramatic is if my metal got a larger radius, let's say I went down a couple shells, if I fought against the same oxygen, that metal would then lose to oxygen a little bit more. It's now more ionic. Not only is the metal more metallic, in this case here, our oxide is actually more ionic in character as well. In terms of conductivity, you always want to think about two things. For conductivity, you have to have charges, and they have to be mobile. So they like asking this question, not a super hard question, but in this case here, let's take Na2O. Na2O in the solid state, it's sort of locked away in this lattice structure, in this repeating pattern, positive, negative, positive, negative. We definitely have the charges, but unfortunately, because we're a solid, we definitely don't have the mobility. We can't swim through the entire picture. Because there is no mobility, as a solid, I'm definitely not going to conduct. However, because we're going to test the acid and base nature by dropping into water, like we've already been saying, water is good to actually break up all of these ionic bonds. It's a lot of bonds, so that's why we would expect it to be a solid at room temperature, really high melting point. But if you manage to break up all the ions from each other, we're going to end up having water stabilizing. Water is a polar molecule. Water has a negative oxygen side and a positive hydrogen side. If it notices that there's sodiums in solution, positives that are so far unstable, water is going to point all its oxygen sides to help to stabilize it. We're going to see this more so in the next lesson. The most common geometry is actually 6 waters come around it. Water overall is neutral, can't get rid of the sodium's +1 charge, but by complexing, by sort of stabilizing with the sodium, it can spread out this charge. We're going to see in chapter 5, energy is released in this process here. It ends up becoming more stable because water is what's called solvating. It's surrounding the metal from all sides. Exactly the opposite happens to the oxide here. Oxide has a negative charge, so water instead will point its hydrogen sides to try to surround it from all sides here to try to counterbalance this charge here. That hydration or solvation will help to stabilize the bits, which is why water ends up as such a good solvent. So in the ionic state here, even though I might still label it Na2O aqueous, I know that in the aqueous state it's actually been dissociated. 2 sodium ions and oxide ions here. Now I have the charges and now I do have the mobility. In that case here it's conductive. In fact, we're going to get even more conductive the more ions that we have. The more ions I can swim around, the more I can carry a current. So let's look in detail at our period 3 oxides again. So far we have sodium oxide and magnesium oxide. Like I said, the most important thing is because they're ionic, water can dissociate these no problem. Because it can dissociate, I'm going to end up generating that O2 minus. We're going to learn in our acid-base chapter, O2 minus is a strong base. O2 minus is really good at releasing hydroxide. So there we have it again. I want to show you that in a little more detail. O2 minus already has the noble gas configuration. It already should be stable, but you notice because it has a lot of electrons, we say it has a lot of electron density. When it comes close to a water molecule, what's ending up happening here is the O actually also coordinate bonds. It's going to donate both of its electrons and actually grab the hydrogen. The bond here, which used to be holding the O and the H, goes back to the oxygen, and we're going to end up, in this case here, this is going to be a one-way arrow because it's strong. I'm going to try to color code these for you here. This is the new bond that I created to the hydrogen and the oxygen here. The 2 electrons that went back to the oxygen are now on here. And you'll notice here now, because I pulled it off as an H+, I just grabbed the extra proton and I bonded it. Now I have a hydroxide, and now I have a hydroxide. And in that case, that's your characteristic base molecule. So that's what's happening. We're going to refer to this one here as a Lewis base because this one here has donated an electron pair. This one here that accepted it is now called a Lewis acid. A little bit weird to think about water as an acid, but as we generalize the definition for acid bases in the next chapter, we're going to see that in more detail. So as it pertains to us in grade 11, you definitely want to memorize these equations here. When it touches water, we know somewhere along the way it produces the O2 minus. The O2 minus steals a proton from water, no problem, and we end up with hydroxide. Very similar with the magnesium reaction here. Magnesium does have a slightly higher charge. Magnesium is a +2, so we can comment that it's not as soluble. It has a much stronger hold on O2 minus, but again, because of that extra stability that water can surround the ion cells, I can get the oxide ion solution, O2 minus. It can produce the hydroxide that I need, and there we go, we form the base. So metal oxides in general, and in this case here, we specifically looked at sodium oxide, magnesium oxide. Let's totally jump over to the nonmetals then. Again, we're going to ignore argon. Argon is a noble gas, so it keeps to itself. But let's look at the other ones here. Now, phosphorus, sulfur, and chlorine are all nonmetals. They're going to be similar in size to oxygen, although one shell bigger, but they're not going to lose as badly as, say, a metal would. They have much higher Z effective. So in this case here, nonmetal with nonmetal, we end up having electrons being shared instead of being transferred. And once we have this sharing, sure, we're going to still want to have a full shell and octet, but we're going to get a lot of other combinations. Here are some combinations that you can think about. When chlorine bonds with oxygen, it's like starting with chlorine. Chlorine's like this. Oxygen's like this. It's coming in. I know they still have to collide, but how many different ways can I actually draw a molecule that actually has a complete octet, so it satisfies octet rule? So there's an example of like Cl2O, that would be this one. You can try drawing for yourself what Cl2O7 look like. These are not the only ones, but these are the ones that we're going to play with. These ones here are definitely covalently bonded because we see that the tug of war is much more even. The tug of war difference is less than 1.8. And because of that, water is not actually able to break up these bonds. Because we actually don't have charges, these are actually just simple molecules. That's why we call them molecular. So even if you manage to be at a really cold temperature, when those London forces are strong enough to actually keep it as a solid, it doesn't take much. They're going to have very low melting points, and they already would have vaporized away. They don't have a really fancy lattice structure, alternating positive, negative. They don't have the stability that water gives it. They're just going to be simple molecules. When I say SO2, I really just mean one molecule SO2. When I say P4O10, just one molecule P4O10. These ones here are not conductive, so again, covalent bonds are strong. When you drop them in water, you can bubble the whole compound into water. It can swim around the water for a little while, but definitely the bond doesn't break, so there's no charges. Again, unfortunately here, it's fair game for them just to ask you, memorize these equations. So they can ask you here, they can give you the reactants in any of these equations and just ask you what are the products. Fortunately, this question doesn't come up very often, but again, it is fair game for them to just be like, predict the products. I always think of it as a very fancy synthesis reaction. I know nonmetals would typically form an acid, SO3, and then basically combine together with H2O, so then H2SO4 or H2SO3. I form a compound that has H, therefore when I'm in aqueous, I'm going to end up releasing the H and then becoming an acid. I want to make a quick comment on the name here. H2SO4 actually came on our green sheet from sulfate. F or pH is fine. Sulfate was ATN as an ending. I would have changed it to the ending sulfuric acid. Let's see if you can test yourself here for SO3. This one here came from sulfite. I think you had that on the green sheet. What did we change the ending to for if it was sulfite? Hopefully you were able to say to me sulfurous acid, OUS acid. And yet you'll notice in your textbook, they actually call both of them sulfuric acid, but strangely enough, they add this Roman numeral. The question here is, why did they rename it, and what is this Roman numeral? In fact, this Roman numeral here is an introduction to what's called oxidation number, or even what's called oxidation state. This one here is assuming the entire compound is ionic. We're going to assign the charges for everything inside. So let's look at it in detail here. Let's look at the molecule H2SO4. In fact, there definitely is an ionic part. The H is a plus. The sulfate is actually covalently bonded. Overall has a charge of -2. This one here does actually have an ionic attraction between positive and negative. 2 pluses will cancel out the 2 minus. They like asking this in paper 1. Which of these compounds contain both ionic and covalent? It would be a compound that actually has a polyatomic inside. What we're going to do here is we're going to cheat a little bit. This is getting a little bit into chapter 9 for next year. Is we're going to say, I know realistically the S and the O are actually not charged, they're sharing electrons, but what if I came along and what if I pretended the entire thing is ionic? So what we're going to do is we're going to have a whole list of rules in chapter 9, just a quick taste of it here. You're going to still say, well, H is usually going to be +1. I have 2 of them, so that's going to give me a total of +2. Oxygen's charge is usually -2. I have 4 of them, that's going to amount to -8. What charge would sulfur kind of have to have so that when I do the 2 plus sulfur minus this 8 here, it gives me the fact that overall my compound is 0. So just a little bit of algebra there for you. You should be able to do that without actually needing to write this equation out. It's like sulfur has a +6. This is not a real charge. This one here is just an oxidation number. It's kind of like sulfur behaves like +6. So later on when the sulfur, the charge goes up or goes down, we can see whether it's oxidized or reduced, whether it's gained electrons or lost electrons. So that's actually the 6 they put here. When sulfur is like a +6, that's the sulfuric acid form. You can verify for yourself for H2SO3. If hydrogen is +1, oxygen is -2, you'll notice these oxidation states are per atom. So even though I do have 3 of them, I still say oxygen is -2 charge. Let's work on the charges. Again, overall my charge is 0. Otherwise, I would need to add up to whatever the charge is. And in this case, you should be able to see 2 + 1 minus E6 is -4. So sulfur has to be a +1 to end up with the overall 0 charge. So it's still sulfuric acid. They don't even use sulfurous acid at all, but they add in that Roman numeral. For oxidation number, here's where it really matters. It has to be the sign first, then the number. So they're going to actually, on the mark scheme, if you put 4+, it says don't award a mark. So in this case here, you want to make sure you always put the plus first, then the 4, rather than 4+. Okay, they're going to mark you wrong for this 4+. The only reason why I think they do that is sometimes for oxidation state, because these aren't real charges, later on we're going to get charges like +8/3. Even fractional charges, they're not really 8/3. But I guess it's easier to read +8/3 versus 8/3+. Okay. So normally I tell people, just always do the sign first. Most times it doesn't matter, but in times that it does matter, like in this case, you'll have it correct. Right? Otherwise, that's oxidation state. In the past, they used to say oxidation state is the Roman numeral, whereas oxidation number is using the digits for it. But now they use them synonymously. Sometimes you'll see it Roman numeral, especially in names. Sometimes it would just be the digit with the number. Especially if it's a digit, make sure you put the sign first, then the number. Okay. On to the back side, just to finish off this lesson here. I know not super exciting. We're going to jump towards this middle aisle. So we knew metal oxides were basic, non-metal oxides were acidic. These ones here are sort of part metallic, part non-metallic. So we'd expect them to have some combination of properties. There's 2 elements that we haven't touched on yet, which is Si and aluminum. The SiO2, this is actually where we get our quartz crystals from, our silica kind of material. SiO2, we're going to see the structure a little bit in the next chapter. SiO2 is actually a large complex network. It's like a lattice. But you'll notice because it's non-metal, it's actually a covalent lattice. It's a giant covalent structure here. You'll notice I put Si bonded to 4 other oxygens. It's just by ratio when you deal with the lattice structure, even though Si is currently holding 4 actual neighbors, it's like every Si by empirical formula. Every empirical formula is just SiO2. Because of this gigantic covalent structure, not only do we expect this to have very, very high melting point, it's going to be a solid under our regular exposure to it here. This one turns out doesn't dissolve in water at all. But we find that a reaction, we can react it with a very concentrated alkali, which is a base. Things that react with base are called acids. But because it's not very good, we're going to call this one here, silicon dioxide is very weakly acidic. It's not really good at bonding unless you have a really strong base willing to react with it. Again, there's another reaction for you to memorize. Okay, it's not the only reaction that demonstrates a property, but you want to be able to quote at least one that shows the weakly acidic nature. Save the best for last here. We have aluminum oxide. Aluminum oxide, you look at where aluminum is on the periodic table. Aluminum is actually sort of right in between where the metals and the nonmetals are. It's getting really close to the stair step. If you look at the electronegativity difference, you can still comment, yes, it is an ionic compound. Because it's metal, non-metal, electrons do get transferred. It is ionic, but being so close to the stair step, it's picking up some covalent nature. So what I want you to picture is ionic is on one side, covalent is on the other side, but I'm somewhere in the spectrum here. I may be, 40% ionic, 60% covalent. I'm going to have some attributes of both. The ionic part we saw would generate the oxide, so it's going to be basic. The covalent part here doesn't break up very easily, so we saw the acidic part of it. So in this case here, aluminum oxide is our one example that shows amphoteric, or you can even call them amphiprotic. There's a slight technical definition. You can read those two there. But basically, we're saying this guy here can behave either as acid or base. It can do both. And what it's going to depend on is what else it's reacting with. For example here, and these are the last two equations for you to memorize for now. For these last two equations, we definitely know HCl is the acid. The aluminum oxide is really generous. Okay, if you're the acid, I'm going to be the base in this first equation. Or the NaOH is now a base, reacted with that very same aluminum oxide. Again, not the only reactions you can do, but it definitely shows the amphoteric nature. So they might say in a paper 2 question, define amphoteric or define amphiprotic, and show equations to justify it. These are two equations that show one of it acting as a base, one of it acting as acid. So finally here, I've left off the notes here just with just a summary of these period 3 oxides. In the old curriculum, they actually did a whole lesson like this on chlorides. Fortunately, that was just memory, so they just totally removed that. So sometimes when you have really old exam questions, you might see chloride equations. You might not necessarily be able to do them, at least in the iteration that you're doing right now. It actually is just the oxides that we need. In terms of the elements themselves, we know we switch from metal to non-metal. That's when we cross over the stair-step line. In terms of the oxide, the whole compound, metal and non-metal tend to be ionic. Non-metal and non-metal tend to be covalent. Aluminum oxide as an amphoteric was somewhere in between. The ionic ones here all form lattice structures, so they're giant covalent structures. The covalent compounds really didn't form charges. These are much simpler molecules. When I said CO2, I really mean just a blob of CO2. It's not actually repeating or anything like that. That's why we use the term molecular for covalent. SiO2 was the one exception. Like diamond structure we're going to see in the next chapter, it's a covalent lattice of Si bonded to 4 oxygen neighbors. For conductivity, we talked about we need charges, and we need those charges to be mobile. The more charges we have, the more conductive we are. So these ionic compounds break up really well. Water stabilizes, solvates the ions, definitely really high conductivity, whereas your molecular solutions don't really break off at all, so no conductivity. Here's that pesky oxidation number. Remember, this one here has to be the sign first, the plus or minus first, the number after. They will mark you wrong if you do it the other way. So make sure you do those two there. Basically, I'm saying sodium oxide. Let's pretend that's ionic. Well, it is ionic. So sodium is +1, no difference there. Magnesium is +2, no difference there. It's only really useful when we actually look at covalent. Realistically, these are not actually charged. But what charge would they have if I pretended it was ionic? For example, oxygen is -2. There's 2 of them. That means sulfur has to be a +4. You'll notice in all this here, I'm trying to do sign first and the number. Over here, Cl2O7, oxygen is -2, times 7 is -14, chloride is +7. There's the sign first and the number. That's the oxidation state. It's kind of like this non-metal actually has this charge. In terms of solubility, like sodium metal, which is only +1 charge, really soluble. Even your covalent compounds bubble into water, no problem. As you start getting higher charges, like magnesium has a +2, aluminum has a +3, because of that higher charge, you're going to have a much stronger hold on your non-metal. So it's not going to be as easy to dissolve, but when it dissolves, you're going to see this sort of transition. The conductivity sort of drops out. Most important for today is you want to remember metal oxides typically are going to be basic or alkaline. Non-metal oxides typically are acidic, even though your silicon dioxide was weakly acidic. It didn't really react with water at all. But the term here, amphoteric or amphiprotic, means it could be acid, it could be base. It's just going to choose one or the other, depending on what the neighbor is. Just as a quick case study here, non-metal oxides, just say to yourself, they tend to form acids. So unfortunately, this in our environment is actually a contributor to acid rain. Our rainwater is actually naturally already acidic. So we have CO2 in the atmosphere. When it touches the rainwater, as a non-metal oxide, we would expect a fancy synthesis. This ends up forming carbonic acid, H2CO3, and the carbonic acid very quickly releases off this H+. So that knocks the pH. The pH of rainwater was supposed to be a pH of 7. That's only at 25 degrees, by the way. But because there's CO2 naturally in the air, because of this extra H+, this guy here can even lose more H+ as well. The pH is roughly about 5.6. pH is on a logarithmic scale, so every step becomes 10 times harder than the one before it. But that pH here is already slightly acidic. We don't call it acid rain, however, until Acid rain's contributors here, I don't know if I wrote it down for you. Acid rain's contributor are other industrial gases, usually call them SOx and NOx, so any ratios of sulfur oxides, SO2s, SO3s, N2Os, and whatnot. And we're going to see, you have them on the back side, SO2 and water ends up forming H2SO3, ends up adding extra acids, let's say NO3 and water ends up forming HNO3, HNO2, lots of balancing, lots of memorizing for those ones there, but definitely you end up seeing, well, these ones here are adding extra acids, and it's only because of these ones that actually knock the pH low enough. Any pH lower than 5.6, we're talking on the order of about a pH 2 or pH 3 or so. That's when we really worry about acid rain, especially if I have limestone material like calcium carbonate. Acid rain will very quickly eat away this chalky limestone material, and it's actually sort of wearing away at some of the building material. So that's what's happening inside our atmosphere. A couple things we can do to solve it. I can sort of minimize how much SOx and NOx I'm actually throwing into the air. I can try to capture it before it escapes, or I can try to sort of solidify it out, precipitate it off before it ends up becoming gas and interacting with the water. So we see another example of this. Nitrogen is about 79% of our atmosphere is pure nitrogen. If it ends up getting oxidized in the sun, it ends up becoming NOs. NO oxidizes further to become NO2s. Again, the key here is a non-metal oxide. These will typically form extra acids, and that's contributing to acid rain. There are some other uses for this. These equations here, they form smog, they form very particulates in the atmosphere as well. Albeit for nitrous oxide, another compound, we know it's going to be acidic, but this is actually used as a very common anesthetic. Let's say you go in for surgery to sort of calm your body. They might give you a laughing gas. That's this chemical N2O. And one of the sort of other features of this, in addition to making acidic rain, is actually it helps calm your nerves a bit. So that's what we'll learn about our oxides. We're pretty close to the end of the chapter. We just have one more section on transition metals and colored ions to go, but that'll be it for now. If you have any questions, just let me know. Thanks, guys.